Okay, for this next section, this is 10-4, inscribed angles. Everything in this section is based off of one central idea. So we have the idea of inscribed angles. Now, an inscribed angle is actually going to be anytime we have an angle that is on a circle, so the vertex is on the circle, and it's going to be intercepting an arc across from it. So in this diagram that you see on your screen here, angle C is an inscribed angle. The vertex is on the circle, and then the sides are chords. Let me minimize this real quick. All right. So again, the sides are chords. So it's any angle in a circle where the vertex is on the circle and sides are chords of the circle. Now, there's a couple main ideas for this. So I'm actually going to go through a lot of the main ideas first before we do anything else. So for this part of it, let's go ahead and go on to the next slide. This is the inscribed angle theorem. So again, if you need to go back to this, I already have these posted. They're in the one folder, the shared folder. I'll also be posting them on Edsby after we're done with this. The measure of an inscribed angle is half the measure of its intercepted arc. So if you look at these three cases, it's the same no matter where that angle is, no matter what it goes through. In the first case, they show it where one of the sides is a diameter. But again, it doesn't matter. If RT is a certain arc there, then S is going to be half of RT. So anytime you look at an angle like this, let's just say, for example, can't find my mouse here. Hold on. Let's say for a second that this angle is roughly 40 degrees. Well, then that would make this piece of it half of it. So this would be 20 degrees. Same thing on the next one. Again, this angle, it's a much bigger angle. It does not include a diameter, but it doesn't matter. Same thing is true. Now you could always go the opposite way as well. So you could also say that this angle here, if this was, let's say 35 degrees, then this arc would be 70 degrees. So the main idea here, and I'm going to write this a little bit different up here at the top, but the angle itself, so the inscribed angle is equal to half the intercepted arc. Now, you can also reverse that so that you could say that the intercepted arc is double the inscribed angle. So same idea, and I'll use a little bit of shorthand here for this next part. So you could also say the inscribed angle, if you times that by 2, it'll give you the intercepted arc. So again, you can do it both ways. So both the theorem and its converse is essentially true if you're to flip that equation. So if you're to take the intercept arc and double it, you get the other angle. If you take the angle and double it, you get the arc. Now, these are a couple of different corollaries that are based on that same idea. So it says corollary 1, 2 inscribed angles that intercept the same arc are congruent. Well, if you look at angle S and angle T both intercept this same arc. So if you say maybe this arc was, say, 40 degrees again, well, then this angle would have to be 20, and this angle would have to be 20. Therefore, those two angles would be congruent. So again, if you have two angles intercepting the same arc, they're automatically the same. For corollary number 2, the inscribed angle in a semicircle is a right angle. Because again, we know that a semicircle is 180 degrees. So if I draw a diameter straight across here, we know that this arc over here is 180 degrees. Well, that's 180 degrees, then this angle is going to be half of that, which makes it 90. So anytime you have a right angle inscribed into a semicircle, it will always be 90 degrees. And then corollary number 3, opposite angles of an inscribed quadrilateral are supplementary. Well, now that one is a little bit different, but it's the same idea. So let me use 2 different colors here to represent this. This arc here, this really big arc, all the way around. And let me pick another color here. And this arc here, I'm gonna go in blue. All right, we don't know the actual measures of those 2 arcs, but I could say that this blue arc is called X. And I could say that the other arc would then be 360 minus X. Well, I know that angle S is going to be half. Angle S is going to be half of X, and angle U is going to be half of the 360 minus X. So together, what would angle U and S be together? Well, we could say if I took the measure of angle S plus the measure of angle U, it'd have to be equal to the 360 minus X plus X divided by 2, because I'm taking half of the one angle and half of the other angle. Well, what happens to the 2 X's? They cancel out. So if they cancel out, I just have 360 divided by 2, so they must be equal to 180. So if you have 2 angles across from each other, since they're each going to be half of the other part, and the 2 arcs together would have to add up to 360, half of that is always going to be 180. So those 2 angles that are across from each other are always going to be supplementary. They're always going to add up to 180. So again, all of these are based off that same idea. Now, the measure, so this is a slightly new theorem. However, it's still based on the same idea. Notice the angle itself, in this case, it's still on the circle. So although this one's not called an intercepted arc, one second. Although this one's not called an intercepted arc, it's still hold on. I got somebody that's saying they're still in the waiting room. Oh no, they're good. They're good. Okay, those were almost gold. All right, I think we got everybody that's supposed to be here. Anyway, the idea here is that we have a angle that's on the circle, so it's still going to be half of its intercepted arc. Even though it's not an inscribed angle, since it's on that vertex, since the vertex is on the circle itself, it still follows the same rule. So we have an angle formed by a chord and a tangent. And in both cases, there's 2 different angles here. Both angles are going to be half of their respective intersected arcs. So angle AED, so the one that they're referencing there in the then statement, this angle is half of its intercepted arc that's over here. Whereas if you went to the opposite side, if I did the angle going this way instead, this angle will be half of this arc. So again, in each case, it still holds true, the same idea, that same theorem. All right, let me go back out to the text and see, were there any questions before I move on from here? Yeah, you can raise your hand, you can type it in chat. Yeah. So far, again, the ideas here are all based on the same main topic. Again, an inscribed angle or an angle formed by a chord and a tangent, they both have that same exact property. The angle is going to be half of its intercepted arc. And that's what this little summary is about. So the corollary, okay, so a corollary is a theorem as well, but it's a theorem based on another theorem. So when it said corollary for that one part, let me flip back to that screen. These are all their own separate theorems and ideas that are based on the main theorem of the angles being half. Because like corollary number one, we can use the other theorem to prove it. So since we know the angles are half of that arc, we can then say, well, if you have two angles that are intercepting the same arc, they must be congruent, because if the measure has to be half of the arc, and I use the example of 40 there, the one angle is 40, so the arc is 40, so the angle is 20. The arc is 40, so the other angle is also 20. They must be congruent. So again, a corollary is just a theorem that's based off of another theorem. All right, I think that was the only other question. All right, let's go back to where we were. So that was the last slide that I had showed you guys. This one, now these are all the examples. So I grouped all the examples together because everything in this section is related in a way that you're basically using the same idea over and over and over, no matter which one of the problems you're doing. So you're essentially doing something that's half or doubling, depending on which way you're going. On the first question, you have given circle P with the inscribed angle S. If RT is 47, what is the measure of angle S? Well, the measure of angle S, again, it has to be half of that intercepted arc. So we're just taking 47. Oops, 47. I don't know why I just wrote 42. 47. Dividing it by 2. And half of that would be 23.5. And that would be our answer. Again, that's all we're doing. That's what the majority of this section is. So out of all the sections in this chapter, this is probably going to be one of the easier ones. If the measure of DG, so here's DG right here, is 45.6. What are the measure of angle E and F? Well, again, E and F must be congruent because they're both intercepting the same angle. So, and in each case, they're going to be half. So if we take the 45.6 and divide it by 2, let's see, 44 would have been 22. So this will be 22.8 for each angle. 22.8. Now, for the next one there, if RT is a semicircle, so they're telling us that RT is a semicircle, and when you name a semicircle, you can either name a semicircle with the 2 points or 3 points. Most of the time, if direction wasn't important, they would tell us all 3. For them just saying that this is a semicircle, it doesn't really matter if they use 3 points or 2 points. So it says RT is a semicircle. What is the measure of angle RST? Well, if that is a semicircle, then we can say that this has to be a right angle. So it's going to be 90 degrees. For angle C, or sorry, for part C, if measure of arc ABC, so now ABC, so we're going from A through B all the way around to C, is 184 degrees. And then let me grab a different color. And then measure of arc BCD, so going from here all the way around over here, so this side is going to be 242. What are the measures of the angles of the quadrilateral? So there's a couple different things that we can do. First off, we know that based on the angle 242, C is going to have to be half of that. So if that's 242, 242 divided by 2 gives us 121. So that's this piece. But if we know that that's 121, the angle across from it has to be, I did what wrong? Let's see what he's saying. A, B, C. Yes, I did. Thank you, Alex, for catching that. Erase, erase. I went the wrong way. Thank you. I think my answer there might hold for one of the angles, but it's in the wrong place. So let's erase that and put it in the right place. All right, so ABC, B, C, D, B, C, D. That's the one that was mixed up. All right, B, C, D, going around the other way. Thank you, Alex. All right, so B, C, D. So this was the 242. So for the work is still the same. So I don't even know why I erased the work. 242 divided by 2 is the 121. That's going in this angle here, which makes more sense because that looks like an obtuse angle. And then the 121 and this angle, those two together have to be 180 degrees. So if I take the 180 and subtract the 121, that'll leave me with 59. So this angle is 59 degrees. Then we have, for the other one, let's do that in blue. So we have 184 for this entire arc. So again, 184 divided by 2. That's going to give us 92. So this angle is 92 degrees. These two, D and B, also have to be 180 degrees together. So subtract the 192 from 180. And that leaves you with 88. So this one is 88. So those are all of our angle measures on that problem. For the next one, so we have another try it there. We have if arc RST, so this arc here is 164. What is the measure of angle RVT? Well, again, RVT is the inscribed angle that's intercepting that arc, so it's just half of it. So if we take half of this, the angle is going to be 82 degrees. On the next one, so SPU, that's going around this way, SP and U. That's going to be 79 degrees. Oh, nope, wrong. That was the angle. Got to be careful with the symbols there. Hold on. Eraser. The angle SPU is 79. So let's try that again. This angle is 79. They want to know what the arc is across from it. So this is, again, we're going backwards. So instead of taking half of it, we're doubling it to get the arc. So 79 times 2 is going to be 158. All right. Any questions so far? Again, raise your hand. Tell me if I did something wrong. I don't see any other questions. All right. If nobody else has questions, let's go ahead and go to the other examples. I don't know why that went that way. All right. On the next one, the try it 3. Given, so now we have some tangent lines. Given tangent, so BD is a tangent line, so you circle P at point C. If AC, so the arc AC, so on my circle, let me highlight it again. I like using colors on this anytime I do it, and I highly recommend using highlighters or colors whenever you do work, if you draw pictures, because it gets a little confusing if you're using the same image for multiple diagrams. Let's see, at C, this is, let's see, 88 degrees, it said 88. What is the measure of angle ACB? So ACB, this angle right here, that's going to be half of it. So that'll be 44 degrees. Given EF, or sorry, EG is tangent to point P at point F. So again, we have that tangent. And it says that GFC is, so angle GFC, GFC. So they're giving us this angle is 115. So they're giving us the angle this time, and they want FAC, the arc. So we're going from the angle to the arc. We're going to have to double that measure. So we have 360. Oh, sorry, not 360. 115 times 2 is going to give us 230. And that'll give us the measure of the arc. Again, if you're given the arc and you're finding the angle, you do half. If you're given the angle and you're finding the arc, you do double. All right, number 4. Given WY is tangent to circle C at point X, what is the measure of arc XZ? All right, so they put the measurements this time on the actual diagram. We have arc XZ is what they want us to find. So they want this arc. So again, the arc will end up being double the angle. So this is 50, this will be 100. For, that may not be a good color to use. For the other side, what is the measure of angle VXW? So VXW, so they're looking at this angle here. Well, we know a couple of things, all right? And we can do this one of 2 ways. We can either use the fact that the entire circle is 360 degrees, or we can use the fact that this straight line is 180 degrees. So we could either, let's do the circle option first. If this is 100 and this is 196, we can take those and subtract it from 360. So 360 minus 196 minus 100. Well, that would give us a total of 164. No, that's too much. Of 64, just 64, I believe. Did I do that math right? Somebody check my work. Just 64, I think. That was almost 200. Yeah, should be 64. All right, so that means that this little arc right here is 64. Well, if that's 64, then this angle is going to be half of that, which would be 32. Now, the other way that you did it, is it 74? Let's double check that. What do I have? 360 minus 100 minus 196. No, that's 64. We're good. All right, so that's 64. Half of 64 is 32. The other way that I was saying that you could do this is use the idea of this line is a straight line, so that's 180. So instead of doing 360 at the beginning, I could have taken the 196 and divided that in half. If we divide that in half, 196 divided in half is going to be simply 98. So this piece would be 98. So we could then say 180 because of the straight line and subtract off the 50 for the one angle and the 98 for the other angle, which would leave us with the 32 for the last angle. So again, 2 different ways that you could approach that problem. Either way, you get the answer of 32. Questions? Okay. All right, these are just additional examples But again, they're all kind of the same idea again and again. Those are kind of simple examples. Let me just go on to the assignment because I don't want to take up too much of anybody's time. And I'm just over 30 minutes right now. So on this page, which is page 467, the section of work for 10.4 is numbers 22 through 31. So again, that's essentially all the ones that say practice on this side. But then stop right there. I don't need you doing all the proofs. I don't want to do any proofs right now. So it's just going to be those. Any other questions for today? Any other questions for today? Again, in case you didn't see my other posts the other day, my hours on Tuesday and Thursday for office hours, I'm having to shift them slightly because of another reoccurring meeting that I'm having every week. So for Tuesdays and Thursdays, I just want to make sure I say this during this time. Office hours on Tuesdays and Thursdays will be from 12:45 to 2:15. So instead of it spanning the one window, because I know some of you guys had told me as well in a couple different messages that some of your other classes were meeting and you couldn't attend any of the live office hours. So by shifting this, now I'm between two different sets of times. So maybe that'll allow more people to join me while I'm doing office hours, but I'll be on Tuesdays and Thursdays from 12:45 to 2:15. And I made note of that on the EDSB page as well. All right. Any other questions? How's my, well, Fernando, we're not really on summer vacation, but it's going okay. All right. Any other questions? All right. Well, have a good one. I'm going to end this. I'm going to post this to EDSB, and then later today, I'll work on reposting the 10.3 section since that recording got messed up.